So, Faraday's law. What is it? How does it work? What does it do? Right. When I first learnt about it, it was quite confusing. And in some ways, it feels like you're walking uphill both ways. But it really isn't. It's really not that confusing once you learn the theory behind it. So depending on your own level of education, in high school they may have just been giving you a formula sheet and you're expected to plug it in. Whereas in university they would have given you like a whole definition with like, oh, these are line integrals and loop integrals and surface integrals and flux integrals and so on and so forth. And today we're gonna explore that a little bit. Maybe not to the full rigor, but certainly enough for you to understand where it comes from, how does it work, right? So fundamentally, what Faraday's law is it relates EMF, which is a type of voltage, denoted by the funny looking E. This is a Greek letter epsilon, with a different number, something called magnetic flux. Basically, think about it's like some unit of area with like some magnetic field going through the total amount of it throughout the entire area, basically. And it's specifically talking about how fast that field changes, right? So the faster one thing changes, the more voltage there'll be on the other side. We're not quite going to touch over the right side of this equation quite yet. We'll touch on it a bit, but the main focus is really on the left side here, on the EMF, because let's say you have a battery, for example. Here is a 6-volt lantern battery. You may have seen like a 9-volt battery. You may have seen like some a D cell 1.5 volt or a triple A 1.5 volt, something like that. So if if you're so inclined, and I'm not endorsing this to be clear, let's say if you just so happen to like the two terminals of the battery, then you're gonna get quite a nasty shock. But here, what it's describing, it's kind of like if you touched one hand on one terminal, you touched another hand on the same terminal, and you still got a shock. And more concretely speaking, what it's talking about here is, let's say if you have like a closed loop of wire, you take a multimeter on, you have a closed loop of wire, you take a multimeter on one point, multimeter on the same point, and somehow you still get a voltage. And the reason why is going to be quite interesting. But let's go over the basics for now. So, what is voltage? Voltage is basically talking about potential energy, right? And more specifically, it's like potential energy per unit charge. Um, but sometimes, let's say if you see on a formula sheet, like V equals like the electric field E times the length L. What does that mean? Think of it a bit like gravitational potential energy. And indeed, you could think of it like actual height, for example. You could map it as height. But let's say, as an example for now, like uphill, you have like one ball at mass m. It's going to be at some height h, right? What's the amount of energy it has stored up in this height in this ball? That's just going to be mg times h, right? And what that means is it's basically mg is of course the gravitational force, but then h is like the height, but that's also the distance that it travels through, right? So same thing happens in general, really. So of course, as you may remember, work, like as in like energy, is equal to your force times the distance over your force travels. And like there's also all kinds of stipulations. You might have seen like some angles or vectors or something, but that's basically the general idea, right? So same thing happens with charges, really. So let's say if you have a charge here of some q, right? Large charge here, maybe it's 1 million electrons. But then here you have some little q, a small amount of charge, and it's right up there next to the other million electrons. That's 1,000,001 in total. It's gonna act a bit like a compressed spring, right? There's some amount of energy between the two. It wants to force, like light charges repel, right? It wants to be forced apart. So we can kind of characterize that amount of energy in the same way. Like when it flies apart, it's going to travel some distance. But that force is going to depend on the amount of distance you've traveled. It's a bit like a spring, really. So let's say if you're pushing up against a spring, like for the first meter, it's pushing with a force of like 1 Newton, let's say, right? Your second meter is 2 Newtons. Your third meter is like 3 Newtons. What you can say is, well, the amount of work for the first meter is equal to like one newton times 1 meter, right? And then number two is going to be like 2 newtons times the meter, and then 3 newtons times the meter, right? And then you can say, well, what's the total amount of force you have? That's going to be, around 6 newtons, something like that. But it's still an approximation. You can get a better and better approximation if you divide this up into millimeters or micrometers. Like if it's infinitely small, it's going to be infinitely precise. But more concretely, you can say, well, let's just say you have a small distance, right? That's more easy to think about, and that's what we're going to stick with. So back to our so back to our charges, right? It's gonna the main charge will produce some amount of electric field, and we want to characterize, well, how much energy there is with the main charge. But if you have, if your little charge, instead of 1 electron, maybe it's 2 electrons, 3 electrons, or 10 electrons even, you're gonna have 10 times more energy, right? Same thing, like previously we've said, your teacher may have said, electric field is just going to be the same as the amount of force per unit charge. Same thing here. We have potential energy per unit charge. So that's called potential, and it's the same thing as voltage, really. So that's just basically going to be like the total amount of voltage you have. So maybe at 1 point, let's say at 1 point you have 9 volts. This is a cube, 9 volts, 9 meters of height. 9 volts, and then here down here you have 0 volts. If you have a charge going from point A to point B, it's going to gain 9 volts times, if it's an electron volt, if it's an electron, it'll gain 9 electrons worth of charge times volt of energy, 9 electron volts. You can have, like, if it's 1 coulomb, it'll be 1 joule, I think, something like that. But more concretely speaking, if we look at the actual situation of what's going on, we can have, maybe we could say, well, we can do the same thing with the springs. We can say, well, let's say you took one step. What is the what is the electric field there is at that step? And maybe it took another step. What is the electric field there? Third step, what's the electric field there? We'll add up infinitely many, or we'll add up very many steps, each one with a very small length, and at that point, we'll have some amount of electric charge. That's what it means to calculate voltage. And indeed, you might have seen another formula. This formula would be for a constant electric field. You may have seen another formula, V equals to KQ divided by R, right? And of course, force is KQ over R squared. This is using this technique brought up to a whole new level. If you've taken calculus 2 with integration and so on, you can follow all the official rules, and you'll get this result just the same. But here we're not gonna get numerical results, but we are going to see the basic intuition behind this concept, right? Taking each step, adding things together. So let's see how that works out. Oh, and one more thing. Let's look at an example of how this adding up behavior works with a point charge. If we start at some starting point, go around a loop, and go back at that starting point, what are we going to get, right? Let's say this is our starting point with some electric field going out this way. Go around a whole loop, right? Each, as we talked about before, each little bit of length is going to have some amount of electric charge on it, right? Or electric field, rather, right? But the key thing here, look, if we have, if the length is this way, the electric field is going from the, is going tangentially, right? The electric field is going straight out, right, radially. Those two are completely perpendicular, right? So we think about the E times L. Those two, there's something called dot products, where technically these are vectors and then they multiply together in a scalar. The important thing is, if they're pointing in completely misaligned directions, they're not gonna come to anything, right? It's gonna be zero. So going around the whole way, what we're gonna get, the voltage here going around a for loop, adding up, accumulating, it's gonna be zero. And maybe this is a contrived example, because everything's at the same distance and so on, right? Let's look at another example, right? Let's say maybe here's our starting point. let's take out like a pizza wedge of a path here, right? So we go inwards, like inwards. We're going to go uphill basically. Um, we're going to gain some amount of potential here, right? So the voltage is going to be positive. But then we go back down. If we go back down, we must have gone down the same amount of the same distance, right? And then once we go back to our starting point, it's going to be zero because we've gone uphill and back downhill. So no matter what we do, this is our voltage is always going to be zero, right? Around a whole loop. Now compare that with before. Compare that with what we said about the EMF, right? The EMF, it should have something to do with magnetic field, and more importantly, it shouldn't be zero, right? If there is a magnetic field, it shouldn't be zero. But that's something we'll get to later. But first, let's look back at our adding up. Okay, so let's look at a more simple example first, right? Let's say we have a mailman going down a street at each house collecting letters, right? Let's say it's going down a street in a straight line, and for each house is going to have a different number of letters. Maybe the first house, Alice, has one letter, Bob has two letters, and then Charlie has one letter again, right? So across these three houses, there would be a total of four letters, right? So we can kind of write this out as a um, a sum of the number of letters per house. Let's call that L of H. Let's call it, and then multiplied by the number of houses, or really multiplied by like each step. The number of houses you walked past each step, and I guess you can really trivial, really in this like really trivial case, you can just say it's one house. You can just say that's one, right? But later on, we're gonna see this notation crop up again, and you don't really need to worry about the notation as long as you get like the basic concept across, right? So let's say instead of like a straight line street, let's say he's going across an entire neighborhood, right? Like there are a bunch of houses here. we can say um, we can say at each house, even though it's going back to our starting point, we can at each house it's clearly going to collect like one letter, two letter, another letter, maybe three letters here, and so on. At even though it's back to a starting point, he's gonna collect some non-zero number of letters because each individual house would have contributed some amount of letters. And I suppose in this case, if this house actually took out one of the letters, like if Alice is delivering to Bob, right? So this would be one letter, this would be minus one letters. But crucially, it's going to add up, and if overall, it's there are more letters collected than there is distributed, then it's going to be a positive number. We can kind of signify this by saying, it's going around a full loop, around the whole neighborhood. We can like write down like a little circle here to signify this is the sum across a closed loop. And of course, like no one in real life would use this notation, but later on we're going to see a different notation. We can say this is a a fancy S for a sum, except this is around, of course, a sum around a full loop of a of like some smaller of some continuous quantity like f of x times a infinitely small. You can kind of think about it as a very small, like but concretely small distance dx, right? And then around a full loop. For some reason, it's called c. I think um, fancy mathematicians would call this a contour integral, but here in physics we just call it a loop integral. That's close enough. You'd see this notation crop up quite a lot, but again, you don't need to worry about the notation as long as you get the basic concept across, right? So in this case here, the number of letters, right? That's a scalar quantity, but later on we might see a vector quantity, which we'll get to later. So let's look at a second example, right? Let's say if we have a let's say we have a plane flying around a hurricane. It's going to be a very non-aerodynamic plane. It's going to be just a box, but it will do. Let's say this is a special plane, no engines. It's just a glider, but it is around like it's very windy around a hurricane, so it will probably stay afloat. Let's say it's going around a full loop, and you can kind of think of a hurricane, the wind there, as a force field, right? Each point in space will have some force ascribed to it. It's a bit like playing D&D, right? Or like Warhammer 40K or something like that. If your little character lands on a grid square, you'll roll a dice, and they'll say your character dealt 3 damage, and you go to the next grid square. There's like 4 damage, and the next grid square maybe there's 2 damage, and you'd add up everything together, right? Same thing happens here, right? Let's say we took some amount of length along the path of the travel of the aeroplane. It's going to have felt some amount of force from the wind, right? The force is going to be like this, and that force going across that force going along a certain length, that's going to work, right? Just like before. And in this case here, let's look at the angles a bit more. So if the hurricane is flowing a bit sideways but also a bit out, it's going to have some completely sideways component and some completely outward component. And if the plane is going perfectly sideways here, this is the plane's um, velocity vector, right? Like the how far it's traveling. Like this is the length vector, this is the force vector. We can add up, for each little bit of length, called let's call it dl for a small amount of length. It's a bit like delta L, and we can add up every little bit of the force component on that bit of length that that length will that length will experience, right? So that's going to be f. And these are technically we have something called a dot product, which is a vector. For now, we can ignore this and say somehow magically we'll multiply two vectors together. It'll give us a scalar, and it will also somehow say how lined up those two are, right? What we can do, just like before, we can add up, we can integrate this across the entire loop. Somehow that's called C, and because it's a loop integral, we have a little circle here, right? So across the entire loop, going from point A around a loop back to point A, each little bit of length is going to have some amount of force. That amount of so that's going to have some amount of work, right? And that work, at no point is it negative. It's always going to be positive. It's always going to add up to something that isn't zero. So it will end up that it will we can integrate this all together, and we'll end up with some amount of total work, right? So that's kind of the idea we're going for. And let's see how this applies to EMF, right? So let's get back to the original topic, right? Faraday's law. So whereas we've seen previously, if we go all the way around the electric field produced by a point charge, we're going to arrive back at where we started, and it's going to be 0 voltage, right? Let's look at a weirder electric field here. This electric field is going to be going around a circle, just like the hurricane we've seen before. And unlike with the point charge where it's going straight, like if we take the loop integral around here, if we pretend that we're an electron, starting at this point, at each little bit of distance we go, like at each little bit of length dl, we're going to have some amounts of electric field at each point, right? So we have some amount of electric field times the small amount of distance dl, and then we can integrate this across the entire loop, right? Back to where we started, and because each point we've accumulated some amount of potential here, each point like the amount of potential we get, it's not going to be zero. It's not going to be negative. It's always going to be positive. It's going to add up to something that's positive. And and just like before, where we have a straight line integral with a point charge, we're going to get a number measured in volts, and it'll act like voltage. Here, it'll also act like voltage. If we imagine this was in a copper wire, right? Each electron would go around a full loop, maybe like through a light bulb, through a motor, something like that, and it will indeed expend that energy and power stuff. It's basically just voltage again, right? So think back to the hill analogy, right? If we do think about voltage like height, what does this kind of act as? Think about a spiral staircase, or maybe like a parking lot, right? Multiple stories. We can go around a full loop, But because at each point we're climbing like upstairs, even though we've arrived at like the same point in space, we've gone, up a level, right? So that's kind of the intuition you have behind this. Now, why does the electric field behave this way? Now, that's actually quite interesting. And now we're going to get back to the other side of the equation. Here we have Faraday's law in like the full kind of expanded form, and you will see a different form if you go like even higher in university. But here we can say we have the same loop integral here again. Loop integral of the electric field times the distance, like the length, dl, right? It's going to be the same as what this phi b means. It's called magnetic flux, and it's basically the amount of magnetic field going into some like defined area, right? Let's say here we have like some really strong field, and here's a really weak field, and here's some like stronger again, right? Um, it'll add up each little point on this area, the amount of magnetic field going through each point, and add it up in total, and it'll give us this number. And the key here, what Faraday discovered was that, and technically he didn't discover this because Faraday was kind of he hated maths, but like I think his assistant or something like that discovered it and named it after him. Not sure, something like that. What he discovered was that if we have a changing magnetic field, a changing amount of magnetic flux, maybe we can change the area, change the field, so on and so forth. If it's the amount of flux is changing, then that will produce an electric field that will go around in a spiral. Now that's actually quite interesting because we have because this will act together with something else. This is kind of like a bonus fact, but you might recall Ampere's law, right? Ampere's law is going to be what is it? It's going to be the same kind of looking equation. If you're maybe not in high school, but if you're in university, you might have seen B dot dl, right? And they would have set this to be equal to like some constant times amounts of current, right? And amounts of current and going through some amounts of surface. Like if let's say this was actually the magnetic field instead, there would have been like a wire going straight through with like some amounts of current passing through it. Now, um, a man named Maxwell, like after like about 100 years after Ampere, a man named Maxwell discovered that, um, and this is going to be a really hand wavy explanation, but a changing electric field will kind of act like current. Not really, but it'll be measured in amperes basically. And what will happen is that he discovered if you have a changing electric field going through some amount of surface, just like the magnetic flux here, if you have some electric flux, it will produce a spirally magnetic field, right? Right. So, but then that magnetic field will itself also be changing. So, if we have a changing magnetic field caused by a changing electric field, that's going to cause another, because of going back to Faraday's law, that's going to cause another changing electric field, which will produce a magnetic field, electric field, back and forth, back and forth. He discovered that this will produce a self-propagating, like self-perpetuating electromagnetic wave. And he discovered that the speed of that is exactly the same as the speed of light. Oh, and by the way, all these talk about loops and circles and stuff reminded me that today is Tau Day 6.28. It's the better circle constant. Heathens might call it 2 pi instead, but arguably pi is actually just tau halves, right? Because what this is that it's the uh, circumference divided by the radius, which is arguably the better way to measure a circle. But yeah, anyways, happy Tau Day, and like and subscribe.